Now can everyone see the screen?
Yes, sir.
Yes, sir.
Okay, fine. So what we are going to see today is we are actually going to have a look at our IS code, that is IS1893, which is used for analysis, seismic analysis of structures, and see various clauses and two different methods of analysis that we are going to explore today. So let us first start with our website and open the IS code. I hope you all have the IS code with you. Have you gone through this?
Yes, sir. Yes, sir.
Okay, fine. So this particular code, criteria for earthquake resistant design of structures, this is only part 1 of total, I think 5 parts, 4 or 5 parts are there, of which is only part 1, which is for general provisions and buildings. And this is the one that we are going to use for our regular buildings analysis. Now let us directly jump into it and see. Initial part is like definitions and all those things will be there. You should go through them definitely and try to understand what they mean. We are directly going to the page number 10 here and clause 6.4.3. So this clause tells that what are the different ways of analysis of a building, a regular building that we have. It says that we have two ways of analyzing a building. First one is so equivalent static method, and second one is dynamic analysis method. The equivalent static method is very simple, and we will see that first. And then within dynamic analysis method there are three subclasses or subtypes, you can say. First one is response spectrum method, second one is modal time history method, and third one is time history method. However, in this particular code only equivalent static method is discussed, and within dynamic analysis response spectrum method and time history method is discussed. So today we will be looking at equivalent static method and response spectrum method. Today we are going to see equivalent static method and response spectrum method. The time history method, it's like you will most likely see it in theory of vibration, because you need to understand all those details over there. So time history method will not be discussed here. Of course there is very little explanation of time history method is available in code as well, but we will not discuss that right now. We will discuss only equivalent static method and response spectrum. So let us start with equivalent static method, and this particular method starts on 7.6 clause, I guess, which is on page number 21. Yeah, equivalent static method. Clause number 7.6, page number 21. So this particular method we are going to see today in this particular class. It's very simple, nothing to bother much about it. What exactly it gives is that I think we have discussed it a little bit on our first lecture when I discussed about the response spectra, that how to consider multi-story buildings. At the end somebody had asked question and I told that there are ways and multiple ways of doing that. So one of them is like equivalent static method, where we take equivalent force. So say for example we have a multi-story building like this, with some mass at each story, or let us say m1, m2, m3, m4, and story stiffness k1, k2, k3, k4. Now the task here is that, see, the building is very simple, it's regular, there are no irregularities and mass or stiffness irregularities that you are now aware of. So those things are not here in this particular structure. So it's a simple regular structure. So in such cases equivalent static method may be used because it's very simple. And what is the main purpose of, or what is the main aim of equivalent static method is that if suppose this particular building is going to be designed in a particular location, maybe say you are going to design it in Delhi. So if this particular structure is going to be designed or located in Delhi, then what is the spectral acceleration? A, or I think sir uses the symbol SA, pseudo spectral acceleration. So what is the spectral acceleration that the building is expected to experience a single single degree of freedom system? So we will find out that thing, and based on that we will decide what is the base shear VB that will be expected to act on this structure, and this base shear will be then transferred, or rather I should say distributed as force at each story. So this will be like F1, F2, F3, F4. Now this you should not be surprised by this, because just rotate it and you will see like it's a cantilever with base shear VB is like this. So if base shear VB should be like this, then what should be the forces? Let us say I want to have forces at these 4 locations. Then what should be the forces at these 4 locations? So those are nothing but F1, F2, F3, F4. So look at this beam itself. So if you calculate base shear VB and then distribute that base shear in some way as F1, F2, F3, F4, then you can design this beam for these forces, isn't it? Now designing a beam for these forces are not the same. Very similar concept is happening over here. That is, you have this base shear VB, you will distribute that base shear VB along the stories using some relation, some expression that at first story there should be some fraction of force, at second story there will be some fraction, third and fourth. And then once I have these forces, then I can find out what are the internal forces into these elements, like base shear, bending moment, shear force and bending moment, or axial forces also. So in all these elements I can find out what are the internal forces due to these forces, external forces. And once I identify the internal forces like shear force and bending moment, then I know how to design this particular beam. If suppose this particular beam has shear force diagram something like this, and bending moment diagram second order, whatever it is, then for that particular element I know how to design, because that's simply a design of beam, isn't it? So that's the whole idea of design here, or that's the whole idea of what we are going to achieve. So the main task is how to find out this VB for given structure and let us say given location. That is obtained using IS code, the codal provisions that we have. So let us go back to our IS code, and here in equivalent static method is one method of obtaining this base shear VB. So let us start. The first point here I want you to understand or notice is that this point. This method shall be applicable for regular buildings with height less than 15 meter in seismic zone 2. Just let me confirm, are you able to see this font, or I should zoom in?
Yes, so you can zoom in a bit. It's very small.
This is fine, right?
Yeah. Yes.
So equivalent static method, this tells this last line tells us that this method shall be applicable for regular buildings with height less than 15 meter in seismic zone 2. So what are the seismic zones that you are aware of? How many seismic zones are there?
2 to 5.
2
Or 4.
2 to
4.
2 to 5.
2 to
2, 3,
4 or
4,
5 to
5.
5? 2 to 4 or 2 to 5?
2 to 5. 2 to 5.
2 to 5. Okay.
2, 3, 4.
And 2, 3, 4, 5 are the 4 seismic zones. Have you ever wondered why there is no zone 1? Why it
After
starts?
Bhuj earthquake, zone 1 and zone 2 was combined.
Zone 1 and zone 2 were merged. Actually, it was like many things were changed. Not even Bhuj earthquake. I think before that it was changed. I am not sure exactly, but zone 1 and zone 2 were merged together, and instead of calling it as zone 1, it was called as zone 2, because earlier IS code that we had was like they were having provisions for zone 3, zone 4, zone 5. So now if you switch everything, zone 5 now becomes zone 4. So then all the provisions need to be adjusted accordingly. So this will be complex. So to avoid that complexity, they kept zone 2, 3, 4, 5 as it is. So now entire IS code as it is can be used, except wherever that zone 1 was there in earlier IS code, that has to be read as zone 2. So that makes things easier. Anyway, so this equivalent static method is applicable only for zone 2, and that too only when the building height is less than 15 meter. So what this tells me, building height is less than 15 meters means is it going towards higher frequency or lower frequency?
Lower frequency. So higher frequency, lower time period.
That's correct. Lower time period or higher frequency. So stiffer structures, as well as only in seismic zone 2, that is, it's like no seismicity at all. Seismic zone 2 means very low seismicity. So very low seismicity and very stiff structure. So based on this itself, you can understand that equivalent static method is very loose method, you can say, and should be used only when these conditions are satisfied. Now this method tells us that the design base shear VB should be given by AH into W, this expression. So this is our very basic fundamental expression, VB equal to AH into W. Base shear VB is given by design horizontal acceleration coefficient value, which is AH, and that is given by 6.4.2 using approximate fundamental natural period TA as per 762 along the considered direction of shaking, and W is the seismic weight of the building as per 7.4. This is what we want to calculate now. So first one, we will try to find out AH, or rather we will find out W first, because that's like seismic weight. Finding out seismic weight is easier. AH will require maybe there are more parameters to discuss. So we will first look at W, how to find out W. And I'm not sure before we go for that, I'm not sure how many of you can appreciate this expression. Have you seen this expression before? Have you seen anything similar to this before?
Yes, sir.
What is that?
Sir, I've used this expression.
Where?
Sir, when I joined coaching, so there I studied some bit.
Okay, fine. That's not the thing that I wanted. See, while discussing the response spectrum, I had told you how to obtain the equivalent force, equivalent static force. So I think I called it as Fs. And what was the expression for that? Anybody remembers? What is the usual expression for force as per Newton's law?
M into pseudo acceleration, sir. Mass into pseudo acceleration.
Mass into pseudo acceleration A, isn't it? So, or I think sir uses M into pseudo spectral acceleration, MSA. So this was the expression. We will use MSA because AH is also there, that is going to confuse us. Now let us rewrite it as SA times M, and instead of mass I want to make it as weight. So SA by G, mg, which is weight. So this SA by G and some more factors will come over here, that I call it as, let us say, AH into W, seismic weight. So that same expression you will see here. AH into W. So same thing what I discussed in the first lecture itself, that this Fs itself is nothing but Vb, base shear, and you find out AH. AH is a function of SA and some other factors also. Those are there actually. I should not write it here as equal to, but let it be. This AH is a function of SA and some other parameters, and this is seismic weight. So now let us discuss first how to obtain the seismic weight, and the seismic weight is obtained as per 7.4. So let us go to 7.4 and here itself. Okay. Seismic weight of floors. So how to calculate seismic weight? So that is, seismic weight of each floor is its full dead load plus appropriate amount of imposed load as specified in 7.3. We will see that. While computing the seismic weight of each floor, the weight of column and walls are fine. So what this tells me is that the seismic weight of each floor here, if suppose this let us say this is floor 1, so seismic weight of floor 1 is equal to dead load, that is dead load plus appropriate amount of imposed load, so some fraction of imposed load, so some percentage of imposed load or some fraction of imposed load. So that is seismic weight 1. And the dead load, you know what is the dead load, that dead load will be the self weight of this beam plus the slab and then imposed load on this slab, plus there are weights or dead load on the columns as well, which are not at any particular story. So you can appropriately choose to club that particular amount of column weight into the floor 1. That is, I can say that half column below this floor and half column above this floor, so this entire column will be clubbed into this floor weight. Similarly, this portion will be clubbed into this weight, floor 2, and so on. And that way the last part you can see only this much. So this will be half of the column will be only added to this weight. So that way we can find out seismic weights W1, W2, W3, W4, and then combine everything, you will get total seismic weight of the building. So that's what the clause tells us. This clause tells us. And what is the percentage of imposed load? That is given by 7.3, and that is again, that will again refer us to table 10, I guess. Let us see. 7.3. Yeah. So design imposed load for earthquake force calculation for various loading classes. Here, the design seismic force shall be estimated using full dead load, that is dead load, plus percentage of imposed load as given in table 10. So table 10, let us go to table 10 now. Here, imposed load, uniformly distributed floor loads in kilonewton per meter square. So if suppose imposed load is up to 3 kilonewton per meter square, then you should consider percentage 25 only. So 25 percentage of imposed load. And if the imposed load is more than 3 kilonewton per meter square, then you should take 50%. So this will be dead load plus 25% of imposed load if it is in between 0 to 3 kilo, imposed load is in between 0 to 3 kilonewton per meter square, and 50% of imposed load if it is more than 3 kilonewton per meter square, that is the imposed load. So that way you can find out seismic weights of each floor and then combine entire all the seismic weights of floors, you will get entire seismic weight of the building. So that is our W. So that's our first parameter in this equation. So this W is obtained. Now let us look at AH, that is design horizontal acceleration coefficient, and that is given as per 6.4.2. So let us go to 6.4.2 and see what this clause tells us. Yes, here. The design horizontal seismic coefficient AH for a structure shall be determined by Z by 2 SA by G R by I. In earlier code it was simply written as AH is equal to ZISA upon twice RG, and this is how I remember it. This is Z and this is 2 ZISA by twice RG, but now they mention it slightly different way, same thing but slightly different way. There is some purpose for that as well. Anyway, so this is the expression for that, Z by 2 SA by G R by I. So as I said, SA by G is there, and this is the additional multiplier that we have, so that we can get AH. What are all these multipliers? So let us look at it. Z is equal to seismic zone factor given in table 3. Now where is table 3? Seismic zone factor. So seismic zone factor, if suppose seismic zone 2 you have 0.1, 3, 4 and 5. So highest seismic zone that we have, for that you have Z value 0.36. That is divided by 2. Z by 2. Then we have R and I. R, or let us look at I in this sequence. I is importance factor given in IS1893. For the corresponding structures, when not specified, the minimum value of I shall be so and so. So it can be 1, 1.5, 3 and so on. So if this is importance factor, it depends on what kind of building we are constructing. Is it a critical structure, or is it regular building like household, or is it like a school or a hospital, which is very important. So depending upon that we decide the importance factor. Then there is R, which is called as response reduction factor, and this particular response reduction factor is also given in this particular code. We will see that. And then SA by G is the design acceleration coefficient for different soil types, and that is given by these expressions here. Okay, so you can see this is given for use in equivalent static method. If you are going to use equivalent static method, you have to use these expressions for SA by G, and that depends upon only time period T. So depending upon time period T, you can find out SA by G. And if you are going to use response spectrum method, then you have to use this. And remember that all these values obtained are for 5% damping. So if your damping is different, then you will have to modify the expressions accordingly, modify these SA by G values accordingly. So now let us see where are the values of importance factor and response reduction factors are given. So these values are given in the table following table 3, maybe 4 or 5 somewhere. Let us see. Here you can see importance factor I, it should be 1, 1.2, 1.5, and for what type of building it should be 1.5, for what type of building it should be 1.2 and 1 are given here. Similarly, there is a clause for response reduction factor, and there will be table for that as well, I think table 9. So let us look at that. Here response reduction factor R for building systems. Movement frame systems, response reduction factor is 3. You can see all the response reduction factor 3, 5, 1.5, 4 and so on. Here you should remember one very important thing is that, you see, if you are using RC building, then there are two classes, ordinary movement resistant frame and special movement resistant frame. So among these, it is specifically mentioned that 4, 5, okay, not here. See note 1, where is it? RC and steel structure in seismic, yeah, RC and steel structures in seismic zone 3, 4, 5 shall be designed to be ductile. Hence, this system is not allowed in these seismic zones. So that means, see here, see note 1. So ordinary moment resistant frames are not allowed in zone 3, 4 and 5. Ordinary moment resistant frames are allowed only in zone 2. And for 3, 4, 5 you need to have special moment resistant frames, this or this, and for that response reduction factor is 5. So difference in special and ordinary moment resistant frame is only about the ductility design or ductility provisions. So whether the IS1893 is properly taken care or not in the design, that is considered in special moment resistant frame or ordinary moment resistant frame. So if you provide proper ductility provisions, then it is SMRF. If you do not have proper ductility provisions, then it is OMRF. So accordingly you can choose response reduction factors. So these are and then only one last thing remaining, SA by G. Where is it? Okay, as I told, I think this SA by G, and let me go back there. So in this equation, Z seismic zone factor, for that you have a table, R you have a table, I you have a table. So from that you can find out SA by G is given by these expressions, and depending upon the type of soil you have to choose appropriate expression here, and it depends on time period T. So if you are using equivalent static method, then time period calculation is very simple, and that is given here. The time period in equivalent static method only, the time period is calculated as, if suppose you have bare moment resistant frame building, that is without any masonry infill, then these three expressions, depending upon the type of RC moment resistant frame or RC steel composite or steel moment resistant frame, you can use this expression 0.07 by H raised to 0.75. If you have building with RC structural walls, you can use this expression. And if you have buildings which do not classify into A and B, then for all other buildings you should use this time period 0.09 H upon root D, where H is the height of the building as defined in 7.6.2a, a particular clause that explains how to calculate height, and then base dimension. And for easy access, the next page itself gives you for various buildings how to find out what is the height and what is the base width. For this type of building, what is the height and what is the base width, and so on. For various types of buildings, you have height and base width calculations, how to find out that value. So that is given here. Okay, so the entire equivalent static method revolves around this equation, VB is equal to AH into W, and how to get each one of them. And for that you need not remember anything, you just start with this particular clause, and then W, I want to find out W. So there itself it is given that you have to now refer to 7.4. So go to 7.4, see how to calculate. Then how to calculate AH, it tells you that go to 6.4.2 and find out how to calculate that thing. So now let us look at how exactly this entire thing can be executed for a structure like this. So let us see, we have a structure like this, and multi-story regular frame. And I want to design this, and let us say the zone is seismic zone, 2, and let us say the height is 3 meter. Each story height is 3 meter, so 3 into 5 15. So just barely matches our criteria, that is it is in seismic zone 2 and total height is 15 meter. So based on this I can say that I can use equivalent static method. So what is the first thing that I need to do? Let us go to the first equation, that is VB is equal to AH into W. I need to find out what is the seismic weight. So to do that, of course, now I need to give you all the details of what is the column dimensions and cross sections, and I mean it's 3D, so I should also provide you what is the third dimension here, that length, as well as the slab thickness and so on. So there will be many details that I have to provide, but let's not get into those calculations actually, because those calculations are very simple. You can just very easily find it out how to do all these calculations. To calculate seismic weight, it will be just like unit weight of concrete or RCC, that is 2400 kg per meter cube, and then multiply that by its volume. So that will give you weight, dead weight or dead load, and then imposed load will be given on each floor. Like let us say here on the first floor, let us say it is 2 kilonewton per meter square. I'm just getting some numbers here. Let us say it is 3.5 kilonewton per meter square, and so on. So if I am considering imposed load for W1, that is the first story, what will be the imposed load I should take? Based on the clause. So let us say I am talking about seismic weight W1. So W1 will be dead load of first story plus some percentage of imposed load of first story, isn't it? So the dead load of first story, it's simple to calculate, like 2400 into volume of the concrete RCC. What is the percentage of imposed load I should take?
25.
Yeah, so 25%, because 25% of imposed load, because it is less than 3. On the other hand, if I am taking it on the second floor W2, then it will be 3.5, that means more than 3. So then in that case it will be for W2, it will be 50% of imposed load. So that's, and then yeah, I forgot to mention one thing here. Let us say on the top floor I have, let us say 4 kilonewton per meter square. Then how much should I consider? 4 is actually very high, it should not be, but just for the sake of numbers I am taking. So this last one, W5, since it is top floor, do not consider the imposed load at all. So there is a clause for that as well in that particular seismic weight calculation. So on the top floor, no matter what is the imposed load, you should not consider it. Do not consider imposed load. Okay, so that way you can find out all the seismic weights, and then seismic weights are found out. Now what we were to find out AH. So the expression for AH is Z by 2 R by I SA by G. So what is the Z value? Can you tell me now, looking at the IS code?
Z is 0.1.
0.1 for zone. Let me check one second here. Yeah, for zone 2, the Z is 0.1, correct. So this is 0.1 divided by 2. Then R by I. So let us first look at I, importance factor, that is somewhere here. What should be the importance factor? It's a simple apartment, residential apartment. Residential or commercial buildings other than those listed in serial number 1 with occupancy more than 200%. Now, do you think that 5-story building will have more occupancy more than 200?
No, sir.
No, sir.
So that with what should be the value then? Importance factor.
1.
1. Yeah. So importance factor should be 1. So this is 1. What about R? Response reduction. It is table 9.
3.
Yeah, you can go for 3 here because it is seismic zone 2. Nobody is stopping you to call it special moment resisting frame and then design as per proper ductility provisions. Nobody is stopping you from doing that, but that is not necessary as such. So you can go for ordinary moment resistance frame, and 3 is our number that we are going to use here. So R is 3 and SA by G. Now how to calculate SA by G? SA by G depends upon
So first time period.
time period, correct. So how to find out time period? Here. So I tell you that it is a moment resistant frame with infill walls. So with masonry infill. So tell me which expression will you use? A, B or C? A is here, B is here, and C is here. Moment resistant frame with masonry infill walls.
A, sir.
A1. This one. Which among these two? These three, sorry.
First one.
Okay, first one. But here bare moment resistant frame, and what is written here in this?
So it is without, sir. So it
It is without. So I told you that my frame is moment resistant frame with masonry infill walls.
So C will be this. C.
Yeah, C is the answer. Because all other building, the masonry infill for RC frame building, this expression you should use. So 0.09 H upon root D. So height of the building. What is the height of the building here?
10 meter.
Height of the building. (15 meter), yeah. And what is the D? So let us look at D. D is base dimension of the building at the plinth level along the considered direction of earthquake shaking in meter. So if you see the next page here, base dimension is D, this dimension at the plinth level. So this kind of structure we have, and I have not provided you with the dimension here. So this, let us say 3 meter itself. So now what is the base dimension? D?
6.
6, correct. So T will be equal to 0.09 H upon root D. Whatever this T is, find out that T, and based on that T, now we will find out. So can you just do this calculation roughly and tell me what is this value? We will see. How much it is? Yeah, 0.55 second. So now let us go to this SA by G expressions, and see where is it. And let us assume that we are on a hard rock. The building is to be designed on a hard rock. So strata is hard rock. So let us look at this. So hard for rocky or hard soil site. So these three expressions. 0.55 is the T. So which expression I should use now here? This second one, isn't it? Because it is in between 0.4 and 4. So if in between these, then SA by G is equal to 1 over T. So what is 1 over 0.55?
1.81.
1.82, something like that. So SA by G is 1.82. That's it. So this will give you whatever the AH value is. Calculate this and tell me what it is. Huh?
0.03.
0.03. Okay. So 0.03 is our seismic weight. Seismic coefficient, and this has to be multiplied. So VB is equal to this 0.03 into seismic weight, whatever you get. That will be your base shear. Now this gives you base shear. So most of the important part that was required from seismic analysis was done here. We have base shear. Now the next task is to distribute that base shear at different floors, so that for that particular forces, then I can find out what are the internal forces, and I can continue my analysis and then continue with the design. So that is achieved. That is also given in IS code here. And distribution of base shear.
.6.3, I think.
What is it?
Sir, page number 23, I think.
Okay, page number. Okay, yeah, that this itself. But I want to start with the actual discussion. See here, this 7.6.3 design base shear computed in 7.6.1 shall be distributed along the height of the building and in plan at each floor level as below. So first, vertical distribution of base shear to different floor levels. So this is what we need to find out, and that is done using this expression, which is this: Qi is equal to Wi hi square over summation of Wj hj square summation over j into Vb, and this Qi is nothing but the design lateral force at floor I. So that means here the forces will be something like Q1, Q2, so on up to Q5. And how that Q1, Q2 up to Q5 is obtained is here. Q1 is equal to W1 H1 square over summation j is equal to 1 to n Wj hj square into Vb. Let me check if I have written it correctly. Yeah, summation 2. So this is the fraction at first story. So you can see this this part is going to remain constant, this part is going to remain constant. So for each floor, only this part is going to change: W1 H1 square, W2 H2 square, W3 H3 square, and W4 H4 square, and so on. Then you will get Q1, Q2, Q3, Q4. So for this building now, for this particular building, I calculated base shear Vb, and now I have forces Q1, Q2, Q3, Q4 and Q5. Now do the regular analysis, any method you want, finite element method, or since the system is simple, you can use classical methods as well. And due to these Q1, Q2, Q3, Q4 and Q5, find out what are the internal forces in beams and column, that is bending moment, shear force and axial forces. And for those bending moment, shear force and axial forces, design the member as well as provide appropriate ductility using ductile detailing by IS 13920.